Okay, so let's start our course today. So, Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all. We have 23 students at the moment. Hopefully, others can join soon. So, what we are going to do today, we will do this divided into two parts. The first part is I'm going to explain to you about the frame modeling, and on the second part we are going to do Ansys demonstration on frame. So that's what we'll do. Okay. By the way, your attendance is on the chat section. Please make sure that you fill in the attendance. All right, so I'm going to go to presentation mode now on frame. Let me do recording first. So I'm going to go to presentation mode now. Okay, fine. So now we are in presentation mode and we are being recorded. So we'll talk frame analysis beginning from today, and what I'm going to explain to you this morning before we go to Ansys session is how we will do modeling using frame. Okay, and also quickly I'm going to talk about the frame equation. So before I forgot, I have to mention that next week will be our last class before you go for your mid-semester break. And after mid-semester break, by the way, mid-semester break is also going to be your cuti raya, right? And then after that, you will have your test week. So you will do your test one, exam one, after the mid-semester break. So that's what we will do. So next week is going to be our last meeting before you go to your mid-semester break. And then after that, straight away, you will have your test week. Then you have to do your test one, which is going to be online test. Okay, so now let's go to our presentation. All right, so far you have done few elements. You have learned springs, you have learned bar, and also you have done truss, and you have um, worked out the quizzes on those elements, those structures. So I feel that by now you have a good understanding, hopefully so, on what finite element modeling and analysis. And also remember last week we talked about orientation, element orientations, and 2 days ago you did a quiz on that. And that element orientation is very important, especially now because you begin to work with frame. And for frame, element orientation angle is crucial. All right, so that's what we discussed today. Before I continue, can you respond to me? You see what we have here on the screen, beam and frame.
Yes.
All right, so what you see over here is two type of structure. On the left, we have beam, and on the right, we have frames. Okay? Uh, Beam can be regarded as a subset to frame. So that's a good way to say that. A good way to explain to talk about beam, which is actually indeed it is a subset of frame. So this is a frame, and beam is a special case of frame. So if you look at the beam here on the left, so this is the beam. Okay? Then you realize that this beam here, it looks like a bar. Okay, it looks like a bar. That it is a straight line, but of course you will notice that the force is what we call as transverse force. Okay? And the consequences of having transverse force is that you will have shear and you have also bending. Okay? So now the force here is not actual force, and because of this is not actual force, then you will have what we call as internal moment and also uh, internal shear force. So this is beam, which you have learned in strength of material. So we have shear, and we have also bending moment. So that is the behavior of beam. Okay? But the structure, if you look at what we have here, then you will observe that all elements is in a straight line. Okay, so that is typical beam. Because of that, there will be no axial force. No axial force. When I'm saying no axial force, I'm talking about internal force here, actually. So yeah, in beam here, you have shear and bending moment. Then that means you are going to have shear force and flexural stress and shear stress. Flexural stress, sometimes we call it bending stress, but you don't have axial force. While in bar, you have axial force, but you do not have shear and bending moment. So that's the difference between beam and bar. So in case I ask you during the test, then you know the difference between what is the difference between beam and bar, what's the similarity between beam and bar. So that's the case. Yeah, so that is beam. Now let's look at on the right side. On the right side, we have frame. Okay, we have frame, and in our frame here, the first thing that you will note is that the frame, the element or the member of the frame, they could have different orientation. So this element here or this component here, okay, it doesn't have the same orientation to the one on the right. This one is horizontal and this one here is vertical. So you remember when we talk about truss, every member, it has different orientation. So in bar, every member, they have the same orientation. So that's a difference between truss and bar. Now here, when we are talking about frame and also beam, you begin to see the difference. So the same here for this large structure, which looks like a frame of a building, right? The frame of a building. Then every component, every member, they have not necessarily the same orientation. And what's the consequences? The consequences here is that in frame structure, you might have axial. So I'm going to write it here. You have shear, have bending, and you have. So that's the difference between what we have here on the left, which is a beam structure. Okay, beam structure. And what we have here on the right, which is frame structure. So I hope you see the difference. All right. So now I'm going to focus now on frame. I'm going to focus now on frame. So let me check if somebody is trying to get in. All right, so now let's come back again to our presentation here. So now you see we have beam element, we have frame element, but our focus is going to be on frame element. But of course, I need to mention beam element first quickly. So again, that is our element equation. Okay, you have two nodes, node number 1 and node number 2, and you see that we have shear force and bending moment in our beam equations. Then that shear force, I call it Fy. So you have Fy at node 1 and at node number 2. That is x-axis, that is y-axis. And of course, you have bending moment at node 1 and at node 2. And of course, you will have also the displacement. Because of this Fy, then you are going to have dy. And because you have moment, you are going to have rotation. Remember, force will lead to translation and moment will lead to rotation. So you see the effect of force and moment. And because of that, you are going to have this force and moment and also displacement over here, which also involve rotation. Right, so it is going to be a 2 by 2. And now you will have your E, modulus of elasticity. You have your L, which is the length of element. And now you have I, which is moment of inertia. Moment of inertia. Actually, to be complete, it has to be written area, moment of inertia. All right, so now you have your equation, beam equation. But that's not, we don't focus on that. What we are going to look at here is this frame element. So remember that in frame element, not only you have bending, but you have also shear force, and also you are going to have axial force. Only now, the axial force and shear force is described as force in X and force in Y. Okay, have force in X and force in Y. Of course, based on vector, this Fy and Fx, all right, can be described into axial force and also into shear force. So this Fx and Fy represent the axial and also the shear force. And of course, you have your bending moment. So as usual, you will have it at each node. That's why you have F1x, F1y, M1, F2x, F2y, and M2. Okay, so those are the forces which also include moment in this case now. And of course, together with the force and moment, you will have your displacement, which now also include rotation. That's why you have at your force matrix F1x, Y, and M1, F2x, Y, M2. And for the displacement, D1x, D1y, rotation 1, and also D2x, D2y, rotation 2. So F matrix and D matrix. What about the K matrix? The K matrix is given by this equation. Yeah, it looks challenging, right? This equation. So how do you calculate? How do we calculate K? Very easy actually, and only that you need to do a lot of calculation, even for this one element, right? So this is our element equation. So our K here, this K here is this. All right, so that is our K. E over L as usual, right? And then over here, you got cross-sectional area A. This is 12, by the way. I is, of course, the moment of inertia. And then you have learned what is C, you have learned what is S, C and S, which you have learned before, sinus and sinus. Okay, what are these empty space? It is not empty actually, only that this is diagonally symmetrical matrix, meaning that this component over here matrix is actually that one, for example, and this component of this matrix is actually this one here. So now you understand that this is symmetrical matrix. All right. Of course, you have learned what symmetrical matrix is, but anyway, This is a 6 by 6. Now, this is important. Theta. That is our theta. So meaning now that is our X global, our Y global, X and Y reference, and that is our X local, which is from node number 1 to node number 2. Because positive X local is from node 1 to node 2, that means you can write your F and D in this way. 1, 1, 1, 2, 2, 2. That's the way you write it. From 1 to 2. The reason is, of course, I repeat again, because positive X local is from 1 to 2. Look at that direction. If that's the case, then that is going to be your theta. That's going to be your theta. All right. So that is the theta that you will calculate for your C and S. Okay. So now, what about now if I don't want this positive direction as such? So now you feel that, okay, I want it to be to this direction. So that would be my X local from 1, sorry, it is now from 2 to 1. Please observe the red color. So now the X local is from 2 to 1. Then that would be your theta. Look at now, the theta is going to be measured in that way. So the K, matrix K, the equations remains the same. Okay, remains the same. Only now that the theta that you are going to use for your cosinus and sinus is going to be based on that theta. That's number 1. Number 2, and this is important, you cannot write it in that way. No, you cannot write it in that way. You have to write it instead f to x, f to y, m2, f1x, f1y, m1, and the same d2, d2, rotation 2, d1, d1, rotation 1. So that's the way you are going to write your force and displacement equation. Why? Because now your X local is from 2 to 1. All right, so that is very important. Now, we go next, yeah? So, what about modeling? What about modeling? So now, let's look at these two structures. Let's look at these two structures. Structure on the left and structure on the right. So now let's do modeling. We begin with the structure on the right. Okay, we begin with the structure on the right. So, as usual, we first start with the node location. What's the rule? If I have the load, I have the node. So I have over here. See, I have the node over there. And also I have the node over here. Sorry. The node over there. If you have support, you have the node. Fine. So I have the node over here. All right. I have the node over there. If you are at the end, you have the node. Then, if you are at different orientation, or the component is changing direction, you have the node. So that means one over here, one over here. That's it. So now you have your node, and then I can put numbering. 1, 2, 3, 4, 5, and 6. Okay, and also element numbering. 1, 2, 3, 4, 5. So I'm going to put circle so that to show that this is element. All right, I hope you understand what I'm doing now. So that is for the structure on the right. Okay, so now what about the structure on the left? We are going to apply the same principle. When you have the load, you have the node. You have the load over here in the form of bending moment. Also here. When you are having support, then you must have the node. Over there. When you are at the end, you must have the node. These are the end, right? But you have already node, so no need to have additional node. Don't forget there is a support here, so you must have a node over here. And of course, we have corner all over here, so I put a node because it is a corner. This is also corner, but I got a node already there because there is a bending moment. So meaning now that no need to have double node. So we are going to put a numbering. 1, 2, 3, 4, 5, 6. And the element 1, 2, 3, 4, and 5. So to differentiate with the node, nice. So now I have my meshing. Okay, meshing in this case to show you that I have the node and I have the element together with the numbering. Now let's compare the left and on the right. Of course, you will note straight away that the meshing, they are the same. Okay, so the meshing, these are having the same meshing, the same configuration of node location, element locations, and also numberings. All right, but of course there are different structure and there are different finite element model. The meshing is similar, but the finite element model is not the same. Why not the same? Because the loads are different. The loads are different, and the supports also different. The supports also different. Over here, the support, you have this one, and that one. Over here, the support is this one only this one. So now, another thing that you need to observe straight away is that the coordinate axis, x going up, y going to the left. So there is nothing wrong with that. In fact, if you have a problem, if you have a question, and in that question, it is specified that the X and Y coordinate axis is like that, don't change it. Don't change it. Don't change it. Remember that this coordinate axis is important, the direction, for you to later on to decide what is going to be your theta. So a lot of time I give you the questions later, many times before that. The coordinate axis is not x to the right and y going up. Many times it is x going up, y to the left, or x to the left, y going down. So it doesn't matter. Okay, and you just have to do your theta accordingly. And of course now it is going to be based on this coordinate axis. So for example, this 1000 here, is actually f3x. Okay, so actually this 1000 here actually is f3x, and the magnitude is minus 1000. All right, I hope you understand that. Look at the coordinate axis direction, okay, and observe that positive is going up. So meaning now that it is going to be negative. What about this 2000? This actually is f5y. Why? Because y is horizontal now and positive to the left. So that means this is going to be minus 2000. So now you begin to have some idea what kind of quiz I'm going to ask you on Monday. All right. And this is very important because if you make a mistake here, in your modeling and also in deciding on what actually is the magnitude of applied forces, you make it wrong here, then whatever you do is going to be wrong. All right. So I hope you understand what we discussed here. What about this 10,000? This 10,000 M, okay, is actually minus 10,000. Unit can be Newton, meter, whatever. So I hope you understand why it is negative, because positive moment, no matter your x and y axis, is always going to be measured positive as counterclockwise and negative when it is clockwise. Okay, so I hope you see what's going on over here. Any question? Okay, do you have any question on this one? Okay, no question. Fine. So remember, all this arrow that you see here, forces and moment, those are positive direction. Positive direction. Okay, if your x and y is in this coordinate. And what important to note is that the moment is always positive when it is counterclockwise. If it is clockwise direction, it is going to be negative. All right, so I hope you see what we have over here. Now let's look at theta. So now we are going to learn about how we are going to determine the value of theta. So for that, we are going to look at this one here. So let's look at element number 4. Okay, so I draw again the meshing here. This is element number 4, which is that one, right? So what about theta? Now, So that is element number 4, which connect node number 4 and node number 5. Please observe this one. So that is the theta. That's the theta. Why theta is measured in that way? Remember, your positive global axis X is vertical upward, right? And I decided that the positive local axis is from node number 4 to node number 5, meaning that the positive direction of X local is downward. That is my X local. Why I do it that way? Very simple reason. Because my own rule, you don't have to follow me, is that the positive direction is going to be from low. Okay, I repeat again, from low node number to higher node number. So 4 is less than 5. Then it is from 4 to 5. Okay, so that is positive X local. Then, of course, theta is going to be measured from positive X global to positive X local counterclockwise. So that's the reason why we have our theta. So from here, then, if let's say now I'm talking about this node 2 to node 3. So that is, for example, this is node 2, this is node 3. I decide positive X local is going to be to that direction, right? And global is, of course, going up. See here, going up. That's going up. That is our X global. Then the theta is going to be measured from positive X global, positive X local, like that. So that is your theta, which is going to be 170 degree. Okay. So if I do it like this, then the theta that we have here is going to be used for our cosinus and sinus. And also, because it is from 2 to 3, I'm going to write F2x, F2y, M2, F3x, F3y, M3, and also displacement D2x, y, rotation 2, and D3x, D3y, rotation 3, for us to fill in here. Okay, so the numbering here is based on from what node to what node on your local axis. All right, I'm going to stop now. Okay, and we are going to have a break. So we are going to start at around 9 o'clock or so. Okay, with Ansys demonstration. Anyway, if you have any question, I'm going to answer any question now. All right, so that means you understand what kind of quiz that I'm going to give you on Monday, and you begin to realize how you will do modeling, analysis for frame structure, which you are going to have that on your test 1 in 3 weeks time. Okay, so I think that's it at the moment. We are going to have a break and see you again around 10 o'clock. Thank you. Okay, so let's continue again. Now we are going to do Ansys modeling and analysis for frame structure. So that's what we are going to do. So that's what I'm going to demonstrate to you this morning. Okay, so I have to go to presentation now. Okay, we have a frame structure here in three-dimensional. So can you see what I have here on the screen? Can you respond to that, please?
Can see, bro.
All right. So this is our case study for Ansys. So we have a three-dimensional frame structure, which is, you see, we have this vertical, we got the horizontal here, and also that is perpendicular to the plane. And you know the dimension. The coordinate axis is as given here. Don't worry about this because Ansys is going to take care everything for you. Orient this angle, everything. And the load is given over there. Also, we know the material is steel as given over here. What else? Now we have three different profiles, meaning the cross section of the frame is not the same. For the vertical member, I have O. For O meaning it's a kind of tube. Look at what we have on the right, O profile. So it's kind of a circular tube. The dimension is given there, outer diameter and inner diameter. And we have for the horizontal member, we got H profile or I profile. That's the dimension given there. And for the last segment, it is a channel or C profile. And the dimension given over here. So that is what we need to do. So if we can finish this today, then we finish it. Otherwise, then we are going to continue on this next week. Okay. So that is our structure. And what about the modeling? So we are going to do manual modeling based on manual modeling, and before we do, let me do our strategy. So when you have you are going to have the node over there. You are going to have the node over here. So this is supposed to be support. I forgot to write it here. But that is our support over here. Okay, so that is support. And we will have the node, of course. Now, if I have different orientation, then must have the node. Over here it is vertical, over here is horizontal, and also here I must have the node. So yeah, so far I have 4 nodes. This is sufficient actually. This is sufficient actually. But I want it to be probably slightly more accurate. So in between, I want to have the node exactly at the mid between this node and that node. Also over here. Sorry. Okay, I can just do it like that. And finally, also over here. So from here, I have all the nodes. Let's say this is node number 1, number 2, number 3, number 4, number 5, number 6, and 7. So Ansys will take care on the numbering, but that is the position that I want. So for example, if I'm reading that node, see here, this node, then the coordinate of this node is going to be x, going to be 2 meters, y going to be 2 meters, and z, this is going to be minus 1 meter. So the coordinate of this node, the one here, is going to be 2, 2, minus 1, right? x2, y2, and z minus 1. Very important that you can establish this location because you need that for Ansys later on, okay? All right, so with that here, then I know the location of every node. I know the element. This is going to be element number 1, element number 2, this is 5, and this is element number 6. So we have 6 elements and 7 nodes. So that's what we have here. Okay, so now because we already map our meshing, then we are ready to go to Ansys and we are going to do finite element modeling, meshing manually. Okay, manually. All right, so that's what we will do. So that is our user space, our working space, sorry. So let's begin. The element type in this case is going to be frame, okay? And in that case, in Ansys, the frame, they call it beam, right? The frame, they call it beam. In our class, we call it frame. Beam in our class is going to be subset of frame, but in this case, it's beam. And in this case, the beam is three-dimensional. So actually, the equation is more complicated than 6 by 6 because it is three-dimensional. Anyway, that is our beam. 3-node 189. Sorry, 2-node 188. We have only 2 nodes for our element at the end of the element. I click OK. I click close. Nice. Now we define our material. Material models. As usual. Why it is 200,000? Because I decided that I am going to use the unit as Newton and millimeter. Okay, so it is going to be 200,000 Newton per millimeter square, and that is my Poisson ratio. Nice. Next, remember that if you look at what we have here, we will have 3 different sections. This is the first section, this is the second section, and that is the third section. So we are going to define 3 different sections of beam. Okay, let's do it. So for that, we are going to go to sections, beam, and then it is common section. All right, so this is where you are going to define your section. So number 1, we will have H beam or I beam, it doesn't matter. And I know the dimension 100, 100, and the thickness is 5. That's what I'm going to do. Where's that? Okay. I'm looking for that section just now. All right, I find it. Okay, so I'll put it name HB. Subtype. Under that, that's what we want to have. And then the dimension is as what we have over here. 100, 100, and thickness as 5. Disappear again. Please observe how I fill in the thing. And then the thickness, 5. Okay, we do it. So H beam, that's the section. If I apply that, then it is going to be there. Okay? You can go to preview. So that is our cross section. And over here, the properties are given by Ansys. The cross-sectional area, moment of inertia in y-axis, z-axis, yz-axis, which you can learn later on. Okay, so that is for, excuse me, for H-beam. Now let's go for tube. So for the tube here, that's what we want. 100 outer diameter, 94 inner diameter. Meaning that the radius is going to be 50 outside, 47 inside. Okay, radius outside 50, radius inside 47. So that's what we will do. So I click comment section again. ID is now becoming number 2, don't forget. And I'm going to say that way, OBIN. And that's what we want. Okay, in a radius, 47. Outer radius, 50. All right, so if you click apply, then it is going to be there. Let's preview. So that's what we have. Inclusive with this is our information on the properties of the section. Finally, we are going to do the last one, which is channel. 100, 100, thickness of 5. Let's do. 3, I call it C-beam. And it is going to be channel C. So we know all the dimension. 100 for all flanges. And thickness as 5. I click apply. You can go to preview, and that's what we have. I click OK. What happened now? What happened now is that I have my element type, which is going to be frame. In this case, we call it beam. I have defined the material, right? And also, I have defined 3 different type of section. Section 1 is H-beam. Section 2 is going to be tube or beam, and section 3 is going to be channel. So with that here, then now we begin to do our machine by we provide the node numbering. So let's redo it. So I'm going to go to modeling, create. I'm going to create nodes. Active coordinate system. Node 1 is going to be at 0, 0, 0. Line. So you see there, I have the node over here. So I'm going to do this meshing based on our scheme over here. So we have done with node number 1 over here, node number 2, 3, 4, 5, and up to node number 7. Okay, so now let's go to node number 2, which is going to be over here. I want to use millimeter. All right, so that's node number 2. Node number 3, thousand. Node number 4 is going to be at this coordinate, 1000 and 1000. Hope I'm doing that correctly. Okay, it is wrong. I repeat again. Node number 4 is at 1000, sorry, 2000. All right, so now it is there. Number 5. Let me think. 2000. You see here, 1, 2, 3, 4, 5. Just like what we have over here. 1, 2, 3, 4, 5. Now we go to node number 6 and 7, which is going to be at negative 1000 and at negative 2000 on z-axis. Let's do it. I think I better do it like that. So I'm now in isometric view, node 1, 2, 3, up to 5. Number 6 is going to be over here minus 1000. And number 7 minus 2000. That's it. I click OK now. Now we have our node complete from node number 1 to node number 7. Next, we are going to do our element definition. Okay, we are going to do our element definition. So for that here, I will go back. Remember that we are going to have element number 1, element number 2, etc. Okay, but we agree first that element number 1 and element number 2 is based on this cross section. Sorry, element number 1 and element number 2 is based on okay, I'm going to change it. So let me, instead of having this is going to be H, and this is going to be O profile over here. And this is C profile. So I changed this configuration. The reason is because I've created this is as as section 1, section 2, so that it's going to be consistent. That's all. It doesn't matter. So now what we will do here is we are going to define the element 1 and 2 based on this H profile, 3 and 4 based on this O profile, and element number 5 and 6 based on C profile. So that's what we are going to do. So now we are going to create a node, but element. But before that, we have to define the element attribute first. So now material is the same, but now I want to have case beam. So that's the correct selection. I click OK. What does it mean? It means that whatever I do is going to be based on H beam and material number 1 and element type number 1. All right. So auto number through nodes like this from 1 to 2 apply, and from 2 to 3 I click OK. So now let's go to 3, 4, and 4, 5. But now it is going to be based on circular tube or tube. I click again, element attributes, and I change this. And through nodes, 3 to 4, 4 to 5. I click OK now. And finally, the last segment is based on T channel, T beam. Okay, then I'm going to do it auto number through nodes. Fine. So we have done our meshing. We have done our meshing. What we need to do now is we are going to specify the boundary condition. So for that, then you have to go to loads. Define loads, apply structural placement on nodes, this node. And then all degree of freedom are 0. What does it mean? It means that because it is clamped at node number 1, okay, it is clamped at node number 1, that means it cannot move in the X, it cannot move in the Y, it cannot move in the Z, and rotation in X, Y, and Z, they are all 0. Okay, while the rest of the node, they can move. The rest of the node, they can move. Okay, nice. So now we come back here. What we need to do now is we are going to define our force on nodes, that node. and it is going to be Fy, because y-axis magnitude is -1000. So now you understand why it is in Fy, it is in Fy, and because it is negative, the reason is because it is going down, while y positive is going up. So that's what we have over here. That's y positive. So with that here, then we have done our finite element modeling. Let me save it first. Now, if you want, you can look at this in a better way by going to Style, Plot Controls, Size and Shape, click on Scale as 1, and then Plot Element. So that's what you have. So if you zoom, if you zoom, then you will notice that indeed it is C channel. Okay. All right. So I hope you can see that it is indeed a C channel, right? And now it's becoming confusing now. Okay. And you can also observe here at the junction that this is actually tube. Over here, C channel. And if I go closer to the vertical one, then actually that is the, all right. I hope you see that. Yep, that is. Okay, so now you see that you can visualize it using a proper cross section. Next, what we do is we are going to run by going to solution. Hopefully it works. Solve current. That's it. Now we have done the modeling, we have done the solution, and now we go to post processing. We got the solution, so we need to read the results. We have only one result for set. And then now let's plot the result, the deformed shape. So you see here, I hope you see that we have over here the displacement. The magnitude of displacement is 137 millimeter. So you see here that it is slightly more than 13 centimeter. So you can imagine that the length of each segment is 2 meters, and the magnitude of the displacement at the end of this structure is 13 centimeter, which is quite big. So actually, this is a bit dangerous because the displacement is rather high. So now let's go to a contour plot. We look now at the displacement from contour, degree of freedom, resultant. I click OK. So you see here, that is our distribution. So the red color here is the top maximum is 13.7 centimeter. Okay. Let's now look at stress. So I want to go to formative stress. And that's the result. The maximum is at the bottom here, just adjacent to next to the support, okay, which is logical, and the magnitude is 100, well, round it up, 160 megapascal, 159, 160 Newton per millimeter square or megapascal. Is it safe? Well, if this is mild steel, then it is still safe. Only that the displacement is rather large to my opinion, but it is safe. Safe meaning that there is no plasticity because it is still below the yield point of mild steel, which is around 200, 220, okay, while this one here is 160. So because of that, then this structure is safe, only that it is a bit too flexible. Okay, so that's our information so far. What about now if I want to list the result? Yes, you could. You just click list, and then you can find the displacement, for example. Then that's what you have at every node. You have only 7 nodes, right? So now we have displacement in X, in Y, in Z, and also the resultant. You can also check the nodal solution on the rotation, just as what you have, what you see over here. All right, so what about the stress? The same. You can go to element solution. You can find the stress, formaces, for example. And that's what you have at every element. At every element. Okay, so over here, what you see is principal stress 1, principal stress 2, principal stress 3, and then I'm not sure what SINT is, but over here I have over here a very important one, equivalent stress, which is formaces. Okay, so that is our stress. Okay, so with that here, then we have done our finite element modeling with frame. Okay, so you can try this at home. By doing this now, you understand this, and of course you can change the section, you can add nodes, you can add elements, for example, so that you will have variation of your structure and modeling. And you are ready to do it because you have seen this demonstration. All right, is there any question regarding this finite element modeling and analysis using Ansys? Do you have any question? Okay, if you have no question, then I think that's it for today. Make sure you have done your attendance. So we are going to meet on Monday, and we are going to have quiz on finite element modeling, 2-dimensional for frame structure. All right, so with that, then I finish this class today, which is combination of we talk about the theory of frame, and also we talk about how we can do finite element modeling on frame using Ansys. All right, so that's it for today. Thank you very much. See you on Monday. Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all. Thank you.